Okay, everybody, in this discussion we're going to talk about how monomer-dimer folding equilibria are different from monomer folding and unfolding equilibria, and how those differences relate to differences in how we deal with the data. So we'll bring up Notability. This is the energy diagram from last time, where an unfolded protein proceeds through a single transition state to a folded protein. This difference in free energy between unfolded state and transition state, delta G double dagger, tells you how fast the protein will fold, whereas this difference between the free energy of the unfolded and the folded conformations tells you the stability of the folded state relative to the unfolded state, which in turn gives you equilibrium constant. And this relationship between delta G and equilibrium constant is the same in a monomer-dimer two-state folding equilibrium as it was for just the monomer. The difference is going to be that in the monomer-dimer folding equilibrium, we're going to have two unfolded monomers come together to form one folded dimer. So suppose these are my two unfolded monomers, and they come together to form a helix bundle dimer or something like that. Now, let's describe that equilibrium constant in terms of the concentration of monomer versus the concentration of dimer. All right? If two monomers come together to form one dimer, and K is the equilibrium constant, we could say that K is also equal to the concentration of dimer divided by the concentration of monomer squared. All right, at any given point. And we can rearrange things to say, well, we'll deal with that in just a second. Now, at the same time, though we're not going to know at any given point at the beginning, we're not going to necessarily know how much monomer versus dimer is present, but we will know, and that won't stay constant through the experiment, but we will know how much peptide we put in solution, and that will stay the same. So the total concentration of peptide is going to equal the concentration of the monomer plus 2 times the concentration of the dimer. Where does that factor of 2 come from? It comes from the fact that in every dimer you have 2 copies of the monomer. So if you had, say, 5 micromolar of the monomer and 2.5 micromolar of the dimer, if you split that dimer up into its monomer components, you'd have 2.5 of each of those monomers, and overall you'd have 10 micromolar peptide. Okay, so we use this factor 2 to account for the fact that each dimer contains 2 monomers. All right, and because of the equilibrium constant, there is a relationship between the concentration of monomer and the concentration of dimer. So, for example, we can rearrange this expression for equilibrium constant to say that the concentration of dimer actually equals the equilibrium constant times the square of the monomer concentration. All right. Now remember, our goal is ultimately to have an expression for fraction folded in terms of equilibrium constant and the total peptide concentration. If you're hearing yelling in the background, it's because my kids are fighting, which is a common occurrence, and we just sort of learn to live with it. All right, so we can substitute this expression for dimer concentration into the equation for total peptide concentration. P equals m plus 2 times K times the square of the monomer concentration. And if we subtract P from both sides, what we really have here is a quadratic equation with this form. K is a constant we need to determine from delta G. P is a constant that we know. It's the total peptide concentration. And with this equation in hand, we can use the quadratic formula to solve for what the monomer concentration should be as a function of equilibrium constant and total peptide concentration. So we're simply going to apply the quadratic formula here. Opposite of B, of course, the B would be 1, so because the m to the power of 1 doesn't have any coefficient, so minus 1. Plus or minus, monomer concentrations have to be positive, so we're going to use the positive sign here. B squared minus 4 times A, which is 2K, times C, which is minus P, all over 2 times A, which is 2K. And we can rearrange that to get, or simplify that just a little bit to get the following expression, 8kp divided by 4k. All right, so what this tells us is if we know the total peptide concentration and if we know or can calculate equilibrium constant, and remember we define that here, then we know at any given point how much monomer is present. Okay. Now I'm not going to substitute in that expression for equilibrium constant, which is just the number E raised to the power of minus delta G over RT. And remember, delta G is something that we're going to calculate. We're also going to remember that P is the total peptide concentration. All right, why do we want to know how much monomer is present in solution? Remember, last time we defined F, which is fraction of the total peptide that is folded. All right, so we're going to use this expression for monomer in terms of K and P to tell us what that fraction folded is. So as an example, I would say that the fraction folded should equal 2 times the dimer concentration divided by P. All right, that'll tell us how much of the total peptide is present in the dimer. And we already know the dimer concentration in terms of equilibrium constant and M. So F should equal 2km squared divided by P. All right. And then And so knowing m and substituting m in here and knowing what p is, we can calculate fraction folded. And fraction folded is related to our variable temperature CD data. And what that means is that we can use our variable temperature CD data to estimate what fraction folded is, and then from that we can calculate K and ultimately delta G. I suppose if you want to see the overall expression substituted in, we could do that. What is, not sure I've done this before. I usually just let Mathematica do the algebra for me. Minus 1 plus the square root of 1 plus 8kp divided by 4k times minus 1 plus the square root of 1 plus 8kp divided by 4k. That should equal, maybe I'll do it down here so I don't run out of space. Let's see, 16. We'll use FOIL to figure out what the numerator should be. That'll be 1 minus 2 times the square root of 1 plus 8kp plus 1 plus 8kp divided by 16k squared. And that will equal our monomer concentration squared. Dang it, after I said we were done, I forgot that you could simplify this just a little bit further, take a factor of 2 out of everything. And if you want to simplify that further, you can. I think in the Mathematica file that I have for you, it is simplified something like this. 4kp over 4k is 1. 1 over 4kp is just that. And then we sort of need to put the 4kp inside the square roots, and if we do that, we would get which we could simplify to the following, and I think this is probably how it reads in the Mathematica file that I've given you for monomer-dimer equilibria. And one other thing I will say is that some of you may be concerned about units. Note that equilibrium constant is going to have units of per molar, whereas total peptide concentration should have units of molar, and therefore the fraction folded is a dimensionless number, because every time you've got a K, you've also got a P, and the units cancel each other out. Checking the units is sometimes a great way to determine whether your math makes sense. And now we're really done.